Overall, we will be discussing about the problem number 3 today. So where we are going to discuss about this, you are having a bar and you are going to apply a force of 600 kilonewton, 150 millimeter from the left end, and the right end you will be having a constraint which is a rigid support. So the free end of this bar cannot move towards this fixed end more than 1.2 millimeter. So the right side displacement is constrained. The maximum displacement allowed is 1.2 millimeter, and the left side end is fixed. So the displacement is equal to 0. And over that one, you are going to apply a load of 600 kilonewton, 150 millimeter from the left end. The total length of the beam is 300 millimeter, and the gap is 1.2 meter. Area of cross section of the bar is 250 millimeter square. That means 250 into 10 raised to minus 6 meter square. Young's modulus is 200 gigapascal and Poisson ratio is 0.3. So how are we going to model it? We will be modeling the geometry of the bar like a single line which is 300 millimeter. That is our part 1. And then we need to model the next support, that is we will be modeling as part 2. So essentially in our problem we will be having two parts. One is the bar and the second one is the support. And the support we will be model as a rigid support. That means even if you apply any force, the support is not going to deform. That is a peculiarity of that one. Then on this deformable body, the bar, we will be modeling like a line with 300 millimeter. So in order to apply the load, we will be doing partitioning so that we will get a point on the middle where we can apply the force. This is how we will be going to model this process. So now, let's take the bar. Whenever you are going to design the bar, so you are having a line. What we need a line with 0.3 meter or 300 millimeter length. So I will be creating a line in Abaqus where the coordinate will be fixed at 0, 0 and 0.30. So I will get a horizontal line which is having 0.3 meter or 300 millimeter length. And the part 2, it's a rigid support. So I will be modeled as a vertical line. So for the time being, what I will select, the coordinate I will select means if you are having 300 millimeter line of this bar, then 1.2 millimeter is a gap. So you can tell that this rigid support is going to be located 301.2 millimeter away from the origin. So the bar, since bar we model like this 0, 0 and 0.302, and then rigid support we will be modeling after that, after 1.2 millimeter apart. So the horizontal position of this vertical line will be equal to 0.3012. So I am just going to create a vertical line where the x coordinate is 0.302 for that vertical line in both points. And let's say the y coordinate I am going to create minus 0.5 to 0. So I will get a vertical line which can be modeled as a rigid body. This is how it is going to do. Then whenever you are going to have some deformation for the bar is come and hit the rigid support. So there is always some contact is going to happen. If it is coming in contact with the support, there is always some contact that has to be designed in the process. So whenever we are having some contact of this bar with respect to support, then you will be having some reaction force is going to be developed from the support. This is how we will model it. So now we will move to Abaqus. So look at the Abaqus. So what we are going to do, we will be going to standard explicit model. So let's just create the work directory. Stop. Problem number 3. So I will just save the file as. So let's say maybe problem 3. So we will create the part. First, we will create the bar. So bar is a 2-dimensional geometry. It's a 1-dimensional geometry. So we name it as bar. Then it is a deformable geometry. Then we are having wire. Then let's say the size, approximate size is 1 millimeter. Click OK. So we get like this. So we just need to create a line. The first point is 0, 0. The second point is 0.3. 0. So the line is created. So it is done. So what we need to do, we need to do a partitioning so that we will get a point at the middle for applying the force. So what we will do, tools, partition, enter the parameter, click OK, done. So 0.5 is a parameter because we need to create a point exactly at the middle of the geometry. Create partition. So we got a point here, click done. So the part of bar is completed. Now what we are going to do, we will be modeling the support, rigid support. So rigid support, I just name it as support and 2D planar. So this is a rigid body. So we are having wire. So approximate size is 1. We are telling like that. Then we need to create a vertical line where the point x coordinate is 0.3012 and the y coordinate is, let's say, minus 0.5. Then the right point you are having 0.3012. Then the y coordinate is plus 0.5. So you get a vertical line like this. You get a vertical line like this. So which actually represents the support. Now suppose what we need actually, the support we need, because the support is since it is defined as a rigid body, it is not going to deform. But we need to fix the support. We need to fix the support so that support will not move whenever the force is going to apply that one. Otherwise, there will be a rigid body motion. If you apply a force, if it is an unbalanced force, there will be rigid body motion. So support has to be fixed in the space. For that one, we need to create a reference point on the support where we are going to fix it. So the reference point you can create like this, reference point, and I will just select the right side point. I will select the right, or I can select this top point where I fix the reference point that I will be fixing, so that the support will never move on the right side when you apply a force. So reference point is fixed here. So now this is support is also completed. And after that, we will go into the property module. And the property module we will be going to create. So the material is steel and mechanical elasticity, elastic 200 gigapascal. So 200 into 10 raised to 9. Then 0.3. Click OK. So after that, we will be having create this section. So we are creating a shield section. So it is beam, shield section like a beam. So what we are looking, truss. Continue. So the material is steel and the cross section area is 250 10 raised to -6 meter square. Okay. So where we need to assign the support, because support we don't need to assign any properties because it's a rigid body. So we need to assign the property for the bar. So here you have assign cross section, assign click. So this is a bar. We will be applying the properties. Click done. So steel section done. So material properties are created. So what is next? Next is in assembly. Assembly, we have to bring both these components into the screen. We are having bar as well as the support, and it has to be kept the distance which we want. But since we created everything according to the geometry, it is automatically going to apply in the same way like in the problem. So we don't need to move anything in the assembly. So you are having bar, then you are having the support. So you can see the bar and the support here. So done. So if you closely look at here, you will see that gap. You can see there is a gap between the free end of the bar as well as the support. That gap is 1.2 millimeter. That is how we create the geometry. So assembly is completed. We will go to the step. So steps, create initial static general. The implementation, we can make everything one. Done. Then we will be moving in the interaction. So what is we are having in the interaction? We are having, whenever the free end is going to move and touch the support, you will be having some contact. That contact has to be defined. So the contact have two properties. One is a tangential properties like coefficient of friction, and the second one is a normal contact. So here we don't have a relative movement between this free end and support along the tangential direction. So friction is not need to define. We need to define only the normal contact. So here you are having some interaction property manager. So create what we are defining is contact. And when you define the contact, here you will see tangential, that depends the friction or frictionless. Then you are having normal behavior. So our free end is going to move and hit the surface normal in the normal behavior. So we just need to define on the normal behavior. So everything is default, nothing to do here. Click. Then after that, what we need to tell the software that which are the surface which is coming in contact. Contact is defined. Now we need to tell the surface which are in contact. So here we have interaction property manager. Create what we need, surface to surface contact. The free end will contact with the support. So continue. So it is asking select the main surface. The main surface is this support. So we will select the support. Click done. Then software is going to ask which side of the support is coming in contact. Now we can see the contact is going to come on the left side of the support. So which is actually shown, it is magneta, not allow. Allow is the other side. So we will select the magneta where our body is or the bar is come in contact with support magneta. Then it is asking to select the secondary type. Secondary type, we need to select the point on the rightmost point of the bar. So I can select a node region, select the point of secondary contact. So we will select this point, the free point of the bar. Click done. So everything is default here. Interaction property has already been taken as default. That's the only property we defined. So click OK. So contact is defined. After that, what we need? After that, what we need is a load. Load, what we need to apply 600 kilonewton at the middle of the bar. So load manager, create what we are looking, concentrated load, mechanical concentrated load. Where we are going to apply at the middle here. Click done. What is the force? It is 600 kilonewton, 600,000. Done. Then the boundary condition we have to apply. The left end of the bar is completely fixed. The left end of the bar has to be completely fixed. So displacement boundary condition. Continue. The left end is going to be completely fixed. So U1, U2, UR3, everything has to be equal to 0. Then what is the next boundary condition? The support should not move whenever you are applying a force. The force is going to be applied from the bar. So if there is no resistive force from the support is going to move right side as per the Newton's law. There is an unbalanced force. So this has to be prevented. So what we will do, we will fix this. We will fix this support here. So that support cannot be moved. And since it is a rigid, it cannot deform also. So what we are going to create is create the displacement boundary condition. So let's say boundary condition is going to create it for support. So displacement. So what we are going to select? We are going to select the reference point. Click done. So where we will fix everything so that support is never be able to move right side. It cannot rotate also. So click done. So we have created boundary condition 1 is for fixing the left end of the bar, and the boundary condition support is for fixing the support. So this is done. So what is next? Next is meshing. Meshing is to be done only for the bar. So we just select the part. We will select only the bar. So how many division we will make? We will make 2 division. So our geometry, we will make it as 0.15. 150 millimeter is the length of the element in our case. So click apply. You can see that it is the bar is divided into 2 elements. Click OK. So then what we need to mesh it. We need to mesh it. Mesh the part. OK, to mesh the part. Done. So now we have to select the element. Now we have to select the element. So here you have an option, mesh control, element type. So select the region to be assigned element type. Select this region. Click done. Then you have to select truss. Click OK. So truss is selected. So what is next? Next is to run the job. So run the job. Click OK. So this is problem 3. That is our job. Continue. OK. Submit. So you can see it is completed. So we will see the result now. It's completed. Now see the result. So when you look at the result, what we need actually, we need the stress. We need the stress. So we need the stress. So 1 by C stress is going to appear here. So what we are going to look at, we will be looking at the sigma x, stress along sigma x, S11. So you can see you are having two elements. So red is showing 200 into 10 Q. Actually it is 2000 megapascal. Somehow it's an unrealistic value depending on the problem. So then you can see here it is compressive 400 megapascal. So let's look at the values here. Query raw values. So node, you can look at the node. So you can see here node number 1. You can see the stress is 1.99 into 10 raised to 9 Pascal. So it is 1999 Pascal. That is the stress which you are going to get. And when you come to the left, right now, with the right hand, you can see that there is a stress, additional stress, because it's a magnetic part of element number 2. The stress is 400 megapascal. 400 megapascal. So look at here, it will be clear here. So it is 400 megapascal. 400 megapascal is the stress on the region, and it is compressive. It is negative, that indicates that it is compressive. So it is compressive. Now what we need the displacement. We need the displacement along x-axis. So we can see the displacement on here, query raw values. So you can see the displacement here, it is 1.2 millimeter. That is the displacement which we have specified. Then you are, let's just look at the second node. Second node is somewhere here. First node, then second node is unable to see. Node number 1, node number 3, node number 2, somehow I am unable to locate it. So we will see it, So another thing which you can observe here, that you can see that the material crosses the boundary. The material crosses the boundary. In the reality, material did not cross the boundary, that we know, because the end of the deformation of the bar has to end at the support. But generally, you need to understand that Abaqus is going to show the deformation in an exaggerated way. It will not show the deformation in the 1:1 scale. If the scale is 1.2 millimeter, in the screen you will not see 1.2 millimeter. Abaqus is going to magnify it. So maybe 20 times magnify it and show it. That is why you can see that even though the displacement is showing 1.2 millimeter, it is crossing the limit. So in the reality, it will never cross. So for seeing that one, you can see that one. You are having some option here, which will give you, I think it's in common, option common. You can see the deformation scale factor. Now you can see auto compute it is 33 times. So which indicate that whatever Abaqus shown here, the deformation of the bar is magnified by 33 times. That is why you can see the free end actually crosses the support. In the reality, it never crosses. It has to be ended on the support. So if you look at the scale, instead of scale is 33, if you look at the scale is 1, it is equal to 1. I will just tell that scale, what I repeat is 1. Then you will see that it is moving to support. So you can see this is the actual picture. Your bar is going to deform, and it is going to deform until the fixed end. Now the deformation is 1:1 scale. So you can see the result. Now let's say look at see. You can see node number 2. You can see the node number 2 is approximately 1.5 millimeter, 1.5 millimeter, 0.00149 millimeter, which is matching with the problem which we solved in the class. Then what we need the reaction force. Just look at the reaction force, RF. So what is looking? We are not looking at the magnitude. We are looking for the RF1. RF1, we are going to look at the reaction force along x-axis. So we will see the reaction force, Curie probe values. So you can see on the node number 3, it is 0. You have to look at the support. Support, I think we did not define. We can just look at here. So reaction force here, you can see the support reaction force is around 100 kilonewton. Reaction force on the support is around 100 kilonewton. And from here on the node number 1, you can see it's around 500 kilonewton. So 500 kilonewton in the negative direction, which indicate that it is actually acting in the negative x-axis. 500 kilonewton, 499,998. So it's around 500 newton. And here also, if you look at it, is also in the negative x-axis, which is indicate that there is a force from the support in the negative x-axis around 100 newton. So even the equilibrium is going to satisfy because 500 plus 100 is equal to 600 kilonewton. That is applied force which we applied on the node number 2 along x-axis, positive x-axis. So even the equilibrium is going to can be applied here, which is obeying. So thank you.